Hello everyone. So in this one shot, I'm going to cover ray optics. So I'll cover all concepts, derivations, and important questions that can be asked in your board exams. So first we'll study reflection of light and then the concept of spherical mirrors, different types of spherical mirrors and the nomenclature that we use for spherical mirrors. Then a derivation of mirror formula and the magnification and the refraction of light where we'll study Snell's law and its application. And then the concept of total internal reflection and the concept of optical fibers. Then we'll study refraction at a spherical interface, then different types of lenses, then thin lens formula, its derivation, and then lens maker's formula, and the magnification produced by the thin lenses. Then power of lens, and then if we connect two or more than two lenses together, then what is the effective what is the effective focal length of that system? Then refraction of light through the prism. So here we'll study all cases like the minimum deviation case and how to derive refractive index of the prism if we know the minimum deviation produced by the prism. Then we'll study optical instruments where we'll study simple microscope, compound microscope, and astronomical telescope, both reflecting and refracting type. And we'll also understand what are the magnifying powers for different optical instruments. So first, let us see what is law of reflection. So if we have given a plane mirror and there is a ray which is incident at a point, let us say O, and O is the point of incidence, and this ray is the incident ray. And if I draw normal at the point of incidence, then the angle made by the incident ray with the normal is angle of incidence, and this is the reflected ray. So the angle made by the reflected ray with the normal is angle of reflection. And according to this law, the angle of incidence should be equal to angle of reflection, and incident ray, normal at the point of incidence, and the reflected ray all lie in the same plane. So that is all about law of reflection. You have to remember this. Now, let us see how we can form image if the object is given in case of a plane mirror. So let us say this is the plane mirror and there is an object. Oh, now we can show any two incident rays on the mirror. So this is the first ray, let us say, and this is the angle of incidence. So this will be the reflected ray, right? Now we can show, we can take another ray which is say hitting normally to the mirror. So in this case, the angle of incidence will be 0. So the angle of reflection is also 0. So the ray will retrace its path. So what we can do, the point of intersection of the incident ray gives us the object, and the point of intersection of the reflected ray gives us the image. So if I backtrace the reflected rays, the point of intersection gives us the image. So when we have to backtrace the rays and to form something, then that thing will be virtual. So in this case, it will be a virtual image. And in this and actually you can say the incident rays are originating from O, so we can say this is a real object. Now let us see another case. So let us say converging rays are being incident on this plane mirror. If this plane mirror was not there, then we can say these rays will converge somewhere here. So actually the rays are not converging at this particular point, so it will be a virtual object. And the point of intersection of the reflected ray gives us the image. So this will be the image, and this will be a real image because actual reflected rays are meeting at this particular point. So we should remember this concept. Right, so now let us see what is the deviation produced by the plane mirror. So what is deviation? Deviation is how much the ray has deviated from its original path. So this ray, the incident ray which is showing by AO, it was going along this line, but it has deviated by how much? That is the deviation, right? So this is the angle of deviation. And if I apply, if you look at this AO A prime, it is just like it is 180 degree. So we can say 2 times I plus angle of deviation will be 180 degrees. So we can say angular deviation will be 180 minus 2i. So you should remember this. Now let us see the spherical mirrors and what are the nomenclature used for spherical mirrors. So spherical mirrors are of two types. One is concave, another is convex. In case of a concave, this side is reflecting. In case of a convex, this side is reflecting. Right. So what are paraxial rays? So rays which makes very small angle with the principal axis. Now what is principal axis? I'll come to this paraxial rays after I define the principal axis and other nomenclature. So first of all, let us see what is pole. So pole is the central point of the spherical mirror, and center of curvature is the center of the sphere of which the mirror is the part of. So this is the center of curvature. And if we draw a ray, or if we draw a line which is passing through center of curvature and the pole, this axis is known as the principal axis. Right? Shown, and it is already shown in this particular diagram. So we know what is principal axis, we know what is center of curvature. Now what is radius of curvature? So the distance between the center of curvature and the pole is radius of curvature, or you can say it is the radius of this hypothetical sphere that we have drawn. Right, and you should also remember an important fact that in case of a paraxial rays, the focal length is half of the radius of curvature. Now let us see what is focal length. So what is principal focus? First of all, let us see what is focus. So if we have rays which is parallel to the principal axis, those rays will converge at a point on the principal axis after reflection. So like in this particular illustration, so the rays which are parallel to the principal axis, they are converging at F. This F is known as the principal focus, and the distance of principal focus from the pole is known as focal length. Now what is aperture? So if we draw the circular outline of the lens, the diameter of that circle is known as the aperture, right? So this is the projection. So the diameter of this will be the aperture of this spherical mirror. Now what is a focal plane? So let me show you what is a focal plane. So let us say this is a concave spherical mirror, and this is the principal focus. Now if we have rays which are not parallel to the principal axis, but they are parallel to each other, right? And so these rays will converge at a point which lies in a plane which passes through the principal focus. So I can draw a plane which is perpendicular to the principal axis, and this point of convergence lies on this particular plane. So this plane is known as focal plane, right? So I hope all of you know what are these nomenclature. So let us now move to the next topic, and that is the derivation of mirror formula. Okay, so before that, let me just give you just guide you about the sign convention, and then I'll derive the mirror formula. So let me take the case of a concave spherical mirror. Now this is the pole, this is the center of curvature, and this is the principal focus. Let us say there is an object which is placed beyond C. Now if I want to measure the distance of this object, so all distances will be measured from the pole of the spherical mirror. If we are measuring distance in the direction of the incident rays, then that distance we have to take it as positive. Okay, right. So to measure the distance of this object, we have to travel in the left direction from the pole. So we can say the object distance, which is denoted with U, will be negative. So in order to measure the focal length of this spherical mirror, we have to travel in the left direction to measure the focal length. So focal length is also negative. If the image is to the left of the mirror, again to measure the image, we have to travel against the direction of the incident ray, because the rays are going in this direction, right? So if you are measuring distance against the direction of incident rays, we have to take them negative. So V is also negative, right? And if we are measuring distances in the upward direction, we have to take them as positive. If we are measuring distance in the downward direction, we have to take them as negative. Now let us derive mirror formula. So again, I'm taking the case of a concave mirror. And this is pole, this is center of curvature, this is principal focus, and let us say there is an object AB, right? So this is the object AB. Now let me draw the ray diagram. So in order to draw a ray diagram, we can have some special rays. So first I'll take one ray which is parallel to the principal axis. Now this ray, after reflection, passes through the focus, right? And we can take one more special ray, a ray which is passing through the center of curvature. Now when a ray passes through the center of curvature, it hits the spherical mirror normally, so it will retrace its path, right? It will retrace its path. Now we know the position. Now we know the position of the image, right? So the point of intersection of two reflected rays will give us the position of A, right? Of position of the image of A. Now this is A prime and this will be B prime. Now I can take one more ray which is hitting the pole. So let us say this is the ray which is hitting the pole. Now the reflected ray will passes through A prime. Okay. So now let us see some similar triangles in this, right? So let me just show some important distances. So AB, the distance of AB from the pole is U, and the distance of principal focus from the pole is, say, F, and the distance of image from the pole is V, and the distance of center of curvature from the pole is R, right? So these are the distances. Now let us consider similar triangle ABP and triangle A prime B prime P. So these are the two similar triangles because these angles are 90-degree, right? And the sides of a similar triangles are proportional to each other. So we can say AB by A prime B prime should be equals to U divided by V, right? So let us say this is our first equation, right? So now, so this is our first equation. Now let us form one more equation. So if I look at the triangle ABC and triangle A prime B prime C, now these two triangles are also similar to each other. So the sides will be proportional. So we can say AB upon A prime B prime is equals to, this will be BC upon B prime C. Now BC is nothing but the difference of U and R. So we can say it will be U minus R, and C B prime is nothing but R minus V. Now this is our second equation. Now if I compare first and second, the left hand sides are equal, so right hand side should be equal. So we can say U by V is equals to U minus R upon R minus V. So we can say UR minus UV is equals to UV minus VR. So from here we can say UR plus VR is equals to 2 times UV. Now we can divide both sides by U and V, right? So let us divide both sides by U, V and R. So if I divide both sides by U, V and R, so this UV will get cancelled out, and in this case R will get cancelled out, right? And we'll be having 1 by V plus 1 by U is equals to 2 by R. And we know that 2 by R will be nothing but 1 by F because focal length is half of the radius of curvature. Once we found this relation, we have to apply sign convention. So in this the direction of incident ray is from left to right, and all the distances U, V and F and R all measured against the direction of incident rays from the pole. So all will be negative. So U is negative, V is negative, F is negative, R is negative, right? So we can, after applying sign convention, so we can write it like this. So apply sign convention. So we'll get 1 upon minus v plus 1 upon minus u is equals to 1 upon minus f, and this will become 1 by v plus 1 by u plus equals, sorry, not plus equals to 1 by f. So this is the mirror formula that is applicable for both convex and concave mirrors. So we have applied sign convention so that the formula is applicable for both types of mirror. Now let us see the formula of magnification. So if you look at this relation, where AB is the height of the object and A prime B prime is the height of the image. So we can say height of the object divided by height of the image is equals to U by V. And what is magnification? Magnification is height of the image divided by height of the object. So it will be V by U. Now apply sign convention. So M will be equals to minus V upon minus U. So which will be, sorry, so it will be V by U. Is it clear? And if we apply sign convention for height of the image and height of the object, so that will be height of the image is inverted, so it will be minus hi divided by h naught. So this will be, so just let me remove this. So it will be minus m. So magnification will be minus v by u, right? So this you have to remember. So it will be minus v by u. And the mirror spherical mirror formula is 1 by v plus 1 by u equals to 1 by f. You must have studied these formulas in class 10, but you haven't studied the derivation for that. Now this is the derivation for that. So we have given an object which is 3 centimeter in height, is placed at a distance of 60 centimeter from the convex mirror of focal length 30 centimeter. Find the nature, position and size of the image formed. Okay, right. So we have given convex mirror. Let me draw the diagram first. And the object is placed at a distance of 60 centimeter. So this distance is 60 centimeter. And focal length is given as 30 centimeter. And height of the object is 3 centimeter. And we have to find the nature, position and size of the image. So first of all, let us take the value of u and f as per sign convention. So this is the direction of incident rays, because rays are coming from left to right from the object, and u is measured against the direction of incident rays, so u will be negative, so minus 60 centimeter. Principal focus for convex lengths is in the direction of incident ray. So if I want to measure the focal length, I have to travel in the right direction from the pole. So focal length is positive, so f will be plus 30 centimeter. Now if we apply mirror formula, we can find the position of the image. So 1 by v is equals to 1 by f minus 1 by u. So f is 30, u is minus 60. So if we take the LCM, it comes out to be 60. So 2 plus 1, so it will be 1 by 20, right? So v comes out to be 20 plus 20, right? So image will be to the right of the pole. So so what is the magnification? So it is minus v by u. So minus of 20 upon minus 60, so that will be 1 by 3. So if magnification is positive, it means the image will be virtual and erect. So we can say image is virtual and erect. If magnification has a magnitude which is less than 1, then we can say we are having a diminished image. So virtual and erect and diminished image, right? So that is the nature. And what is the size of the image? So height of the image divided by height of the object is 1 by 3, and height of the object is 3 centimeter. So height of the image will be 3 times 1 by 3, so it will be 1 centimeter. Right, so now let us see the next question. So when an object is placed between f and 2f of a concave mirror, would the image form be real and inverted, or real or virtual? Second, diminished or magnified. Now let us see. So we have a concave mirror, and this is 2f and this is f. An object is placed between 2f and f. So we know, if you have remember the ray diagrams that we have produced for different positions of the object in class 10th. In this case, the image will be real and inverted and magnified. Now let us see how we can derive this by using the mirror formula and magnification formula. So in this case, I can take, this is u, right? And this will be v, let us say. So u can be taken as minus x, where x is the distance of the object from the pole. And since we have a concave mirror and the incident rays are going in the right direction, so focal length will be negative. So I can take focal length as negative f, right? Now let us apply mirror formula. So 1 by v is equals to 1 by f minus 1 by u. So let us substitute the values with proper sign. So minus f minus of minus x. So we can say it comes out to be minus 1 by f plus 1 by x. So if we simplify this, it will be f minus x divided by fx. So v comes out to be fx upon f minus x. Now if you look at this closely, focal length is less than x, right? So it means v comes out to be negative. If v is negative, it means the image is formed to the left of the pole. And now let us see the magnification. So what is the magnification? It will be minus v by u, and it will be minus of fx divided by f minus x divided by u, and u is minus x. So this negative will get cancelled out, x will get cancelled out. So we are getting f upon f minus x. So can you see the denominator is smaller than the numerator? So it is greater than 1. So if it is greater than 1, if magnification is greater than 1, then it means the enlarged image will be formed. So magnified image will be formed and the image will be real, right? It is real and inverted and magnified image. Right. So now let us see, and it is the same question, right? Now let us see this question. An object AB is kept in front of a concave mirror as shown in the figure. So it is placed beyond C. Complete the ray diagram and showing the image formation of the object. Ray diagram is quite easy, and I think all of you know how to draw the ray diagram. So let me show the ray diagram first. This is the concave mirror, and this is center of curvature, and this is the principal focus. An object is placed beyond C. So this is AB. So if I draw ray diagram, so let us take some special rays. So I'm taking ray which is parallel to the principal axis. Now this ray after reflection passes through the principal focus. And one ray we can take which is passing through the center of curvature. Now this ray after reflection from the mirror will retrace its path. And this will be the image produced. So A prime, B prime. So the image will be inverted, real, diminished. So how will the position and the intensity of the image be affected if the lower half of the mirror reflecting surface is painted black? So if you paint the lower half of the surface, the position will not change, but the less rays are able to form the image. If less rays are able to form the image, the intensity will get lower down. So intensity will decrease, but the position will not change. So that is the answer of second part. So why are convex mirrors used as a side view mirror in vehicles? So it is again class 10th question, and it was asked in one of the board exams of class 12th. So we use convex mirror because they always produced virtual and erect and diminished image, and it also gives us the greater field of view. So first, virtual and erect image for every position of the object. Second, diminished image, which provide greater field of view. So we'll be able to see a greater view of the traffic behind us. So do remember this. Now let us see the next question. So calculate the distance of an object of height h from the concave mirror of radius of curvature 20 centimeters so as to obtain a real image of magnification 2. So we have a concave mirror, right? And magnification is given, and we have given a real image. So when do we get a real image? When the magnification is negative. when we get a real and inverted image, right? So m will be negative, so we can say m will be -2, and radius of curvature is 20. So focal length will be 10 centimeter, half of the radius of curvature. So we have to find the location of the image. So magnification is given to us, focal length is given to us. So now let us apply magnification formula, which is minus v by u is -2. So we can take v as nothing but 2u. So now let us apply mirror formula. So 1 by v plus 1 by u is equals to 1 by f. And in this case, the focal length will be negative, so -10. So 1 by 2u plus 1 by u is equals to -1 by 10. So this will be 3 by 2u is equals to -1 by 10. So this will give us 5. So u comes out to be -15 centimeter. This negative sign indicates that the object is to the left of the pole. And so we have found the position of the object. So what is the position of the image? So that will be twice of this, so -30 centimeters. So that is the position of the image. So use mirror formula, explain why does a convex mirror always produce a virtual image. Let us see. So we have a convex mirror. So I'm solving part B. And let us say there is an object which is placed at a distance, say x. So we can say u will be -x. Focal length is positive, right? In case of a convex mirror. Now if we apply mirror formula, so we can say 1 by v is equals to 1 by f minus 1 by u. So this will be 1 by f minus of -x. So this comes out to be x plus f upon fx. So v comes out to be fx upon f plus x. So v is positive, right? So this is positive. And what is magnification? So that is minus v by u. So minus fx upon x plus f, and x is -x. So this negative will get cancelled out. X will get cancelled out. So this will be f upon x plus f. Now magnification is positive. So it means the image is erect. And the denominator is greater than the numerator. So it is less than 1. So it means the convex mirror will always produce diminished image. So that is the explanation for the second part. Right, so now let us see the next question. A mobile phone lies along the principal axis of a concave mirror. Show with the help of a suitable diagram the formation of its image. Explain why magnification is not uniform. Let us see. So we have a concave mirror and mobile phone lies along the principal axis, right? Let us say this is the focus and this is the center of curvature. And we have placed a mobile phone. Let us say this is the mobile phone. And mobile phone is placed between center of curvature and the principal focus. So if I want to show the position of A, position of the image of A, let us draw the ray diagram. So I'm considering a ray which is parallel to the principal axis. Right, and after reflection it will pass through the focus. Now let us consider another ray like this, right? So this is the, we can say this is the image. So this will be A prime, let us say. Now let us draw the image of B. I am taking this point as B. So this ray will be same, right? So there will be no change in this ray, a ray which is passing through the focus. Now let us see a ray which is, now in this particular case, the image of B will formed at C only, because this B lies at a distance of say R from the center of from the pole. So its image will be here only, right? Let me show you. I'm showing this ray. Clear? So this will be B prime. So if I join, so if I show the shape of the image, so this is the shape of the image of the mobile phone, right? So why we are having a distorted shape? This is because the you can say the distance of different points on the mobile pole are at different distance from the pole, and we know that magnification changes with the distance. So that's why we are getting this kind of a distortion. I hope it is clear. Right. So now let us see the next question. So how is the focal length of a spherical mirror affected when the wavelength of the light used is increased? So focal length of a spherical mirror. So focal length does not depends upon the wavelength of the light. It is independent of that, because what we have seen, what is focal length? If there is a plane, if there is a spherical mirror, so rays which are parallel to the principal axis, they will converge at a point which lies on the principal axis. Even if you change the medium, there will be no change in the principal focus. So focal length does not depends upon the wavelength of the light. Right, so now let us see the next concept, which is law of refraction. So before understanding this law, we should know what is the refractive index of a medium. So we'll denote refractive index with mu, and it is defined as the factor by which the speed of light in vacuum get reduced in that particular medium. So it is defined as the ratio of speed in vacuum to the speed in that particular medium. So C is 3 into 10 raised to power 8 meters per second, and V is speed of light in medium, and mu is the refractive index of that medium. Okay, right. So when the light ray enters from a rarer to a denser medium, a rarer medium is having less refractive index, denser medium is having more refractive index. From rarer to denser, the bending of ray is towards the normal. So the ray bends towards the normal. So I can show it like this. Let us say this is a rarer medium and this is a denser medium. A ray of light is coming like this, and this is the angle of incidence, and it will bend towards the normal. So this is angle of refraction. And if the ray enters from a denser to rarer medium, it will bend away from the normal, away from the normal. So I can show it like this. So this is, say, denser medium. This is rarer medium, and this is the interface which is separating them. So it will bend away from the normal. So this is R and this is angle of incidence. Okay, now what are laws of refraction? So there are two laws. First, the incident ray, the refracted ray, and the normal at the point of incidence all lie in the same plane. And the second law is the ratio of the sine of angle of incidence to the sine of angle of refraction is constant. So for example, if this medium is having refractive index mu1 and this medium is having refractive index mu2, so it says that sine of angle of incidence is equals to or divided by sine of angle of refraction is constant, and this constant is equals to refractive index of the medium of refraction with respect to the refractive index of medium of incidence. So it will be mu2 by mu1, where mu2 is the medium of refraction and mu1 is the refractive index of the medium of incidence. So you have to remember this, or we can remember it like this. So mu1 sine I is equals to mu2 sine R. Right. So now let us see the concept of total internal reflection. So TIR stands for total internal reflection. And when do we have TIR? Let us see. So we have given a source. So this is our source and the rays are coming from the source. And this source lies in a denser medium. So this is a denser medium. Here we have rarer medium. Let us say the refractive index of denser medium is mu d and refractive index of rarer medium is mu r. So I'm going to show some incident rays. Let us consider this particular ray which is hitting the interface normally. Now this ray will enter the other medium without getting deflected, right? Now let us see another ray. Now we have increased the angle of incidence, and we know that when the ray enters from a denser to a rarer medium, it will bend away from the normal. So it will bend somewhere in this direction. Now if we further increase the angle of incidence, let us say for this particular angle, and I'm calling it as C. So at this particular angle, the angle of refraction comes out to be 90 degree, right? And if you further increase the angle of incidence, there will be total internal reflection. So if this angle is I, then the angle of reflection is also I. So what is the condition for total internal reflection? The angle of incidence on the interface should be greater than the critical angle. And what is critical angle? It is the angle of incidence at which we'll get 90 degree as the angle of refraction. So if I apply Snell's law at point A, so we can say sine C times mu D should be equals to mu R times sine 90 degree. So from here, C will be sine inverse mu R upon mu D. So that we can remember. So what is the condition for TIR? So let me write down that. So condition for TIR. So first condition is source should be in the denser medium, or you can say the incident ray should come should enter from a denser to a rarer medium, right? Should be in denser medium. And second, the angle of incidence should be greater than the critical angle. I should be greater than the critical angle. So these are the two conditions which gives us total internal reflection. Yes, and sometimes we have to find the radius of the circle of illuminance. Now let us see what is radius of circular of illuminance. So if we look at this interface in 3 dimension, so this is a planar interface, and there is a source which is placed at a distance d inside the denser medium. So if I show the rays which are hitting the interface at critical angle, so if this angle is C, so the ray will graze the interface, right? Similarly, I can show a ray like this. Similarly, we have a locus of all the points. If the ray hit at the periphery of this circle, then the refracted ray will grazes the interface. The refracted ray will graze the interface. Now this circle is known as the circle of illuminance because only through this circular region the rays are coming out. So let us find the circle of illuminance. So this height, let us say, is D, and this is the radius of circle of illuminance. If this angle is C, then this angle is also C. So if I apply tan C, it will be perpendicular upon base R by D. So it will be D tan C. And we have seen what is sine of C is mu R upon mu D. So tan C will be mu R upon root of mu D square minus mu R square. Now if you substitute here, we'll get D mu R upon root of mu D square minus mu R square equals to R. So if we divide numerator and denominator by mu R, so we will get D divided by root of mu D by mu R square minus 1. So this is the radius of circle of illuminance. So we should remember this derivation also. Okay, right. So now let us see some illustrations. So for the same value of angle of incidence, the angle of refraction in three media A, B, and C are 15 degrees, 25 degree, 35 degree respectively. In which media would the velocity of light is minimum? So we know that velocity is inversely proportional to the refractive index, right? So in let me just draw one particular case. So same value of angle of incidence, the angle of refraction in three media. So let us say this is a medium of refractive index mu, and let us consider a refractive index mu A here. So this is medium A. So angle of incidence is I, and we have given angle of refraction as 15 degrees. So this is given as 15 degrees. So if we apply Snell's law for medium A, so it will be mu sine I should be equals to mu A times sine 15. Similarly, for other media, we'll be having mu B sine 25, and then we can say mu C sine 35. Because mu sine I will remain same for all the three media. We are only changing the medium of refraction. And we have to find, so we can say if this is some constant k, so k divided by sine 15 will be mu A, and k divided by sine 25 will be mu B, and k divided by sine 35 is mu C. And we know that sine is an increasing function from 0 to 90. So it means mu A is greater than mu B, and it is greater than mu C. And we know that speed is inversely proportional to the reflective index. So velocity in A will be less than velocity in B is less than velocity in C. So that should be the relation. So in which media would the velocity of light is minimum? It will be minimum in the medium A. So that we should remember. So when monochromatic light travels from one medium to another, its wavelength changes, but the frequency remains same. Explain. Right. So when light enters from one medium to another, the frequency is the property of the source which is generating that light. It does not depends upon the medium. So that's why the frequency doesn't change, but the wavelength change because the speed changes, and speed is nothing but frequency times the wavelength. So frequency is not changing. So if speed is changing, so lambda has to change. Right. So now let's see the next question. How does the refractive index of a transparent medium depends on the wavelength of the incident light used? And okay, right. So we know that speed is lambda times frequency, and speed is speed of light in a medium is given by c divided by the refractive index, right? So so we have given. So how does the refractive index of the transparent medium depends upon the wavelength? So frequency doesn't change. It does not depend upon the medium. C is also constant. So we can say refractive index is inversely proportional to the wavelength. So velocity of light in a glass is 2 into 10 raised per 8 meters per second, and in air it is 3 into 10 raised per 8. If the ray of light passes from glass to air, calculate the value of critical angle. So in glass, so refractive index of glass will be 3 into 10 raised per 8 divided by 2 into 10 raised per 8. So it will be 1.5. So that is the refractive index of glass. And we have to find the critical angle for glass air interface. So the critical angle will be sine inverse refractive index of a rarer medium, that will be air, divided by refractive index of the denser medium, that will be glass. So and the refractive index of air is close to 1. So we can write this as sine inverse 1 divided by 3 by 2. So it will be sine inverse 2 by 3. So that is the answer of the second part. A point source of monochromatic light S is kept at the center of the bottom of a cylinder of radius 15 centimeter. The cylinder contains water to a height of 7 centimeter. Draw the ray diagram and calculate the area of the water surface through which the light emerges out. So basically they are talking about the area of the circle of illuminance. Right, so what we have given? So we have given radius. Bottom of the cylinder of radius. So there is a cylindrical region. So this radius is given as 15 centimeter and it contains water up to the height of 7 centimeter. And there is a point source which is kept at the center of the bottom. So here we have a point source at the bottom. So draw the ray diagram and calculate the area of water surface through which the light is emerging out. Okay, right. So if I show a ray which is hitting normally to the interface, it will passes through the interface undeviated. Now there will be a ray, if we incident this ray at a critical angle, then it will graze the interface. Now this is the radius of the circle of illuminance and we have to find the area bounded by that circle. And R, as we have seen the formula, it is d divided by root of mu d upon mu r square minus 1. Now what is d? So d is 7 centimeter. And in this case, mu d is 4 by 3 and mu r is nothing but 1. So 4 by 3 square minus 1. So this will be 7 times 3 divided by 16 minus 9. That will be root 7, right? So it comes out to be 3 root 7 centimeter. Now if you want to find the area, so area will be pi r square. So pi 9 times 7. So it will be 63 pi centimeter square. So that is the answer of this question. So now let us see this illustration. So state the necessary condition for producing TIR of light. So that we have already discussed. Draw a ray diagram to show how specially designed prism make use of the total internal reflection to obtain image of the object by deviating ray first through 90 degree and second through 180 degree. Now let us see. So if I consider a right angle prism and let us this angle is 45 degree. This is also 45 and this is 90 degree. And if there is an object which is placed parallel to one of the face, so this is A and this is B. So if I show a ray which is coming from A and it is normally to the vertical surface, and if the if the angle of incidence which is 45 degree, if 45 degree is greater than the critical angle, then we can say there will be a TIR. So this ray will come out. Similarly, if I show the ray coming from B, it will follow this path, right? So the image will be like this. So this is the image. Sorry, it should be the other way around, like this. So this is the image of A and this is the image of B. So by using this arrangement, we can deviate the ray by 90 degree. Now let us see one more case. So for this, how we can deviate through 180 degree. If I place this prism like this, so this angle is 90 degree, this is 45 and this is 45 degree. Now let us consider the object. So this is the object AB. Now this is the ray which is coming from A. Again, I'm assuming that the critical angle is less than 45 degree. So this angle of incidence is greater than the critical angle. So there will be TIR. Again, there will be TIR here. So this angle is again 45 degree. Okay, so if I show the image of B, so like this is the ray from B. So here the angle of incidence is greater than the critical angle. Again here the angle of incidence is greater than the critical angle, so there will be TIR. So this is the image of B, so B prime, and this will be the image of A prime, so it will be like this. So like this we can deviate the ray and form the images. This is the answer of first part, and this is the answer of second part. Right, so now let us see the next question. A ray of light falls on a transparent sphere with a center C as shown in the figure. The ray emerges from the sphere parallel to the line AB. Parallel to the line AB, and find the angle of refraction at A if the refractive index of the material of the prism or the sphere is √3. So refractive index is given and A is the point of incidence. So ray is entering from air to this sphere which is having refractive index √3. So this basically is the normal at the point of incidence. So if we apply Snell's law, so we can say 1 times sine 60. So that will be √3 times sine r, where r is the refractive index of the sphere. So sine 60 is √3 by 2, and it is equals to √3 times sine r. So from here r comes out to be 30 degree. So it means the ray will bend towards the normal, and this angle is 30 degree. Now this is the normal at the second point of incidence, right? At this particular point. And by triangle property, this angle has to be 30 degrees. So the angle opposite to equal sides are equal. So this is 30. And the ray, so this angle of emergence will be what? So again, if we apply Snell's law at this point, A comes out to be 60 degrees. So we have to find the angle of refraction at A, and which is 30 degree. I hope it is clear. Now, what is an optical fiber? Let me show you the schematic of that. So if I consider a medium like this, and let us say there is a coating of different material. Right, so this is known as the cladding, and cladding is made of a material which is rarer as compared to this material. So this is cladding, which is having refractive index, let us say μ2, and this material is having refractive index μ1, and I can call it as core. So core has a refractive index μ1, so and μ1 is greater than μ2. So what happens if there is a ray? Let us say there is a ray which enters this optical fiber like this, right? So this ray will undergo multiple total internal reflections, and this ray can exit this optical fiber from the other end, right? So like this, by using this arrangement, we will be able to send signals from one end to the another end over long distances without much losses. So this arrangement is an optical fiber. Right, so the next concept is a prism. So what is a prism? Let us see. A prism has two refracting faces. Let me call it as P. This is Q and this is R. Now this is the first refracting phase, and this is the second refracting phase. And this angle is known as the angle of prism. So A is refracting angle or angle of prism. Now if you take a monochromatic light, let us say we are taking a red light. So this is the angle of incidence, right? And let us say the ray bends like this. So this is the angle of refraction R1. Now the angle of incidence on the second refracting phase is R2. And this is the emergent ray, and it makes an angle E with the normal. So in prism, uh, if we want to find the relation between the angle of prism and R1 and R2, so there is a quadrilateral, right? A cyclic quadrilateral. This angle is 90, this angle is 90, and this is A. This is R1 and this is R1. So this angle will be 180 degree minus A. So since it's a cyclic quadrilateral, and if I consider this triangle, let me call it as M and this is N. So this point is M, this is N. So in triangle M and O, let me take this point of intersection as O. In this right angle, in this triangle, it's not a right angle triangle. In this triangle, sum of the angles will be 180. So we can say R1 plus R2 plus 180 minus A should be equals to 180. So from here we can say R1 plus R2 should be equals to angle of prism. So this is one relation. Now let us find what is the deviation produced by the prism. Now this is the incident ray and the emergent ray. So the angle of deviation is the angle made between between the emergent ray and the incident ray. Now this angle is angle of deviation. Let me just magnify this. So this is the incident ray, and let us say this is the emergent ray, and this angle is angle of deviation, and this point is M and this point is N. And just let me show you, and this is the refracted ray. Now what is this angle? This angle will be, this is R1 and this is the normal, right? So this is I, so this angle will be I minus R1. Similarly, this angle will be E minus R2. So in this triangle, if I call this as O prime, so in triangle O prime MN, angle of deviation will be sum of the interior opposite angles. So it will be equals to I minus R1 plus E minus R2. So this can be written as I plus E minus R1 plus R2, right? So I plus E, and R1 plus R2 is nothing but A that we have just calculated. So do remember this formula. So this is the formula of angle of deviation produced by the prism. So it is I plus E minus A. Now let us see if we vary the angle of incidence, how the deviation changes. So if I draw, on the y-axis we have angle of deviation, on the x-axis we have angle of incidence. So if I plot the graph, it will look like this. First the deviation decreases, and at particular value of the angle of incidence it will become minimum, and then it increases, right? It is not a parabola, right? So let us say this is the value of I, which is the minimum value of I, and at this minimum value the angle of emergence is 90 degree, and at this particular value, at minimum deviation, so this is minimum deviation, at minimum deviation angle of incidence is same as angle of emergence. And if I consider any general point, let us consider this particular point, right? So at this, the angle of incidence is X and the angle of emergence is Y. Similar, and the angle of deviation, let us say, is del prime. And then we can say there will be another point, another angle of incidence, which will give us the same deviation, right? So in this case, the angle of incidence will be Y and the angle of emergence will be X, because angle of deviation is I plus E minus A. So if we interchange I and E, we will get the same deviation. So we have to remember this. Similarly, at the extreme right, the angle of incidence will be 90 degree and the angle of emergence will be equals to I times I minimum. So do remember the nature of this graph. And now let us see the condition for minimum deviation. Now, if this is our prism, so PQR, and this is the angle of prism. So when we have minimum deviation, First, the angle of incidence is equal to the angle of emergence, and the reflected ray will be parallel to the base. So angle of incidence will be same as angle of emergence. So first condition of E will be equals to I. If E is equals to I, we can say the minimum deviation will be 2I minus A, right? And second, we can say if this is M and this is N, Mn will be, ray Mn will be parallel to the base of the prism. And we know that if I is equals to E, then this R1 will be equals to R2 by Snell's law, right? So third, we can say R1 is equals to R2, and both are equals to A by 2 because their sum is equals to the angle of prism. So if that is the case, right? If that is the case, so by Snell's law, if I apply Snell's law at the point of incidence, that is M. So Snell's law at M in minimum deviation case. So we can say sine I is equals to mu times sine R1, and R1 is A by 2, and I can be written as, so from this equation I can be written as delta minimum plus A by 2 plus A by 2. So let us substitute these values in this equation. So we can write mu as sine del minimum plus A by 2 divided by sine A by 2. So again, very important relation. You have to remember this, and there can be a derivation for this in your exam. Now, if we have a thin prism, so what happens in case of a thin prism? So in thin prism, we can, so I will be small, right? For small I, for small angle of incidence, we can say deviation will be small, right? If deviation will be small, we can say del minimum plus A by 2 sine of that will be nearly equals to del minimum plus A by 2. Similarly, sine A by 2 can be written as A by 2. So mu, which is will become del minimum plus A by 2 divided by A by 2. So from here, minimum deviation will be mu minus 1 times A. Right? So you can remember this also, but I haven't seen any question based on this concept. So now the next concept is the dispersion of white light. So what is dispersion? It is the splitting of white light into its component 7 colors. So let me show you. So we have given a prism, and we have incident white light on the first refracting phase. Now this light will split up into its component color. So I'm showing the red light, which is least deviated, and then I'm showing the violet light, in which the deviation is the greatest. Now if I want to find the deviation in red light, we can say if this is the original direction, so this angle will be the deviation in red light, and this angle is the deviation in violet light. And why do we have different deviation for different colors? Because the refractive index, it depends upon the wavelength, right? So we can say there is a relation between the refractive index and the wavelength, and greater the wavelength, greater the wavelength, then we can say smaller is the refractive index for that particular light. So in case of red light, for red, lambda for red is greater than lambda for violet. So we can say refractive index for red will be less than the refractive index for violet. So it means in case of violet, the deviation produced will be maximum because it will bend more because the refractive index will be more. So do remember this relation. And the other colors, or you can say, if I show the deviation produced in the yellow light, so deviation produced in the yellow light is known as the mean deviation produced by the prism. So this will be del V. So do remember this. So this can be asked in your exam. So why the deviation in violet is greatest and in red light it is least. So how does the angle of deviation of glass prism vary if the incident violet light is replaced with the red light? Let us see this question. So we know that in case of a minimum deviation, the refracted ray is parallel to the base. So this is P, this is Q, and this is R, and this is M, and this is N. And if I show the case for, let us say, red light, this is red light. So let me show it with red color. And let us say this is the angle of incidence, and this is the angle of refraction. So here, whether we have red light or a violet light, the angle of refraction will not change because Mn is parallel to the base. So R will be fixed. So we can say sine I is equals to mu R times sine R, right? And if I want to write this equation for the violet light, so it will be sine I prime will be equals to mu V times sine R. So this sine R and this sine R will be same because the reflected ray will be parallel to the base. So we can clearly see that in case of a violet light, the refractive index is more. So mu V is greater than mu R that we have just studied in the last section. If mu V is greater than mu R, then we can say I prime will be greater than I. So the angle of incidence in case of violet light will be more. So how does the angle of minimum deviation of the glass prism vary? So we can say the minimum deviation will be given by 2I minus A, since and so we can say greater the I, greater will be the minimum deviation. So in case of violet, the minimum deviation will be more. Okay, right. So let us see the next question. A ray PQ incident normally on the refracting phase BA is refracted in a prism BAC made of material of refractive index 1.5. Complete the path of the ray through the prism. From which phase will the ray emerge? So let me just draw a magnified view. Right, so this is given to us. This is a 90 degree, it is 60, so it will be 30 degrees. Now there is a ray which is incident normally like this. So it will passes this slant phase without any deviation, and the angle of incidence will be, so this angle is 60 degrees, so this will be 30, right? So 30 is the angle of incidence. Now let us see what is the critical angle. So critical angle will be sine inverse 1 upon 1.5, and I can write this as sine inverse 2 by 3, which is sine inverse 0.67. So critical angle, we can say it is greater than sine inverse 0.5. And what is sine inverse 0.5? It is 30 degree. So we can say critical angle is greater than 30 degree. So if critical angle is greater than 30 degree, so we can say this angle of incidence is less than critical angle. So the ray will undergo refraction at this vertical phase. So it will bend away from the normal like this. And what is this angle? So let us, this angle is R. So we can say 1.5 times sine 30 should be equals to 1 times sine R. So 1.5 times 1 by 2. So from here it will be 3 by 4. So R will be sine inverse 3 by 4. Got it? So from which phase will the ray emerge? It will emerge from the vertical phase. So, and we have already justified, right, why it will emerge, because the angle of incidence is less than the critical angle, right? So three rays of light, red, green, and blue, are incident on the face AB of a right angle prism as shown in the figure. The refractive indices of the material of the prism for red, green, and blue are 1.39, 1.44, and 1.47 respectively. Which of one of the three rays will emerge out of the prism? So again, we have to check for TIR. So let me first take the case of blue light. So blue light is coming, so it is incident normally on the vertical face, so it will just pass this face undeflected. Now, since this angle is 45, so we can say the angle of incidence is nothing but 45 degree. Now we have to check whether this angle of incidence is greater than critical angle or less than critical angle. And we have given for blue light, the refractive index is 1.47. So what is the critical angle? So it will be sine inverse 1 upon 1.47. And this value is less than sine inverse 1 upon 1.414. 1.414 is nothing but root 2, right? So we can say angle of incidence is greater than critical angle. If angle of incidence is greater than critical angle, we can say there will be TIR. So this ray will undergo total internal reflection. Similarly, if we compare green light, again the angle of incidence will be 45 degree. So critical angle for green light will be what? Sine inverse, and this is for green, right? So 1 upon 1.44. Again, this is less than sine inverse 1 by root 2. Again, the angle of incidence is greater than critical angle. Clear? So again, there will be TIR. Now let us see the last case, red light. So light is coming, the angle of incidence is again 45 degree. Now in case of red light, what is the critical angle? So it will be sine inverse. Now here for red light, the refractive index is 1.39. So 1.39. Now this is greater than sine inverse 1 by root 2. So it is greater than that. So we can say critical angle is greater than angle of incidence. So we haven't reached critical angle. So it means there will be refraction. So this ray will pass through this face AC away from the normal, right? So this will be R. So which one of the three rays will emerge out of the prism? So we can say the red light will emerge out of the prism and the other two lights will pass through the face, pass through the base. So this is the justification for this question. So let us see the next question. A ray of light incident on an equilateral prism. So we have given an equilateral prism of refractive index root 3. So this is 60 degree and it is root 3. Moves parallel to the baseline of the prism inside it. Find the angle of incidence for this ray. So it is saying the refracted ray moves parallel to the base. So it means they're talking about the case of minimum deviation. So we have to find the angle of incidence. If this is angle of incidence, then this R will be nothing but A by 2. So it will be 30. So we can say sine I is equals to root 3 times sine 30, and sine 30 is 1 by 2. So I will be 60 degrees. Right? So angle of incidence will be 60 degrees. Now let us see this question. Trace the path of the ray of light passing through the glass prism ABC as shown in the figure. If the refractive index of the glass is root 3, find out the value of the angle of emergence from the prism. So this ray will pass AC undeflected. This angle is 30. So this is again 30, right? Now if we apply Snell's law at this particular point, so we can say sine 30 degree times the refractive index root 3 will be equals to sine R. So it will be root 3 by 2 times sine R. So R will be 60 degree. So we can say this ray will move away from the normal and the angle of refraction will be 60 degree. right? So that is the answer. A ray of light passing through an equilateral triangular prism from air undergoes a minimum deviation when the angle of incidence is 3/4 of the angle of prism. So angle of incidence is given as 3/4 of the angle of prism, and we have a case of minimum deviation. So we have to find the speed of the light in the prism. So let us find the refractive index. So mu formula is sine times okay, right. So let me apply Snell's law. So if I apply Snell's law, this angle will be a by 2, and this angle is given as 3 by 4a, right? So what we can say, the minimum deviation will be 2i minus a, and I is given as 2 times 3 by 4a minus a. So this will be 2. So we have a by 2. So minimum deviation is a by 2. And what is refractive index? It is sine del minimum plus a by 2 divided by sine a by 2. So this will become how much? So we have sine a by 2 plus a by 2 divided by sine a by 2. So 3 by 4. So this will become sine 3 by 4a divided by sine a by 2. 3 by 4, yes. Is it clear? And it is a equilateral prism. So we can say A is 60 degrees. So this will become sine 3 by 4 times 60 divided by sine 60 by 2. So this will be 15, and sine 45. So sine 45 is 1 by root 2, and sine 30 is 1 by 2. So we have 2 by root 2. So it is root 2. So refractive index will be root 2. So what is the speed? So speed of light in the prism will be speed of light in vacuum divided by the refractive index. So 3 by root 2 times 10 raised to power 8 meters per second is the answer of this question. Now let us see the refraction at a spherical interface. So we have given an interface, a spherical interface which separates two media, and this is the axis. And here let us say we have a refractive index mu1, and on this side of the on the concave side we have refractive index mu2. So let us say there is an object which is placed on the axis. So this is the object O. Now let us take the center of curvature as C, and R is the radius of curvature. Now if I consider an incident ray, let us say at this particular point M, we are considering an incident ray. So I'm showing this with different color. So this is the incident ray. And if I draw the normal at the point of incidence, then this will be the normal. And this is the angle of incidence. And let us say the ray bends towards the normal, and I'm assuming mu2 is greater than mu1. So it will bend like this. So we can say this will be the image, because there will be a ray. If ray hit normally to this interface, it will pass undeflected, and we will get the image at I, at this particular point where these two refracted ray coincide. Okay, right. So this angle will be the angle of refraction, and let us take this angle as alpha, this angle as beta, and this angle as gamma. And here we are taking some assumption that we are considering only paraxial rays which are making small angle with the principal axis. So if rays are paraxial, then all these angles will be small. So we can say if all angles are small and if this is P, then we can treat PM is perpendicular to the principal axis. And we can write alpha as PM divided by this distance. Let us take this distance as U, and this distance is R, and the distance of the image from the pole as, or from the center of the interface as EV, right? So I'm taking this as V. Okay, right. So alpha can be written as a PM by U, and similarly beta can be written as Pm by R, and gamma can be written as Pm by V. So if we consider triangle MOC, then I is the exterior angle. So we can say I is equals to alpha plus beta. Similarly, in triangle MCI, we can say R will be beta minus gamma. Now let us substitute the values of alpha and beta in these equations, alpha, beta and gamma in these equations. So I will be written as Pm will be common, so 1 by U plus 1 by R. Similarly, R can be written as Pm will be common, so 1 by R minus 1 by V. Now we can apply Snell's law. So we know that sine I times mu1 will be equals to mu2 times sine R. Since angles are small, we can write sine I as I and sine R as R. So let us substitute the value of I and R in this equation. So we have mu1 times Pm times 1 by U plus 1 by R equals to mu2 times Pm times 1 by R minus 1 by V. Now this Pm will get cancelled out. And now we have an equation. So let us take R terms on one side. So we have mu1 by U plus mu2 by V is equals to mu2 minus mu1 by R. Okay, now we have to apply sign convention. So the distances measured in the direction of the incident ray will take them as positive, and the distances which are measured against the direction of the incident ray will take them as negative. So in this case, U will be negative, R will be positive, and V is also positive. So let us apply sign convention. So we can write mu1 by minus U plus mu2 by plus V is equals to mu2 minus mu1 by R. So we can say mu2 by V minus mu1 by U is equals to mu2 minus mu1. So that is the equation that we have to remember, and we can find the position of the image produced by the spherical interface, where mu2 is the refractive index of the medium of refraction, and mu1 is the refractive index of the medium of incidence, and R is the radius of curvature. Now let us derive lens maker's formula by using the concept of refraction at a spherical interface. So I'm taking a case of a biconvex lens. So this is the biconvex lens, and let us say there is an object O which is placed on the left side of the lens, and this surface has a radius of curvature R1, and this surface is having a radius of curvature R2. So again, I'm going to consider an incident ray. Yes, so this is the incident ray, and let us say for the left, so lens basically is made up of you can say two spherical surfaces. So the center of curvature of left spherical surface, let us say it is C1, right? It is here. So if I draw a normal, and let us say the image is being formed somewhere here. So this is, say, I1. Now this I1 will act as the object for the right spherical interface. So ray is going like this. And let me take some important distances. Let us say this distance from the lens, it's a thin lens, right? This distance is U, and this is R, and let us say this distance is V1. Now let us consider the center of curvature for the right refracting surface. So if I draw the normal here, let us say this ray further get converged like this, right? And this is the final image. Let me call it as I2. And we can say this distance will be V2, or we can take it as V only. Now, if we apply the formula of mu2 by V minus mu1 by U equals to mu2 minus mu1 by R for the left refracting surface. So we can, for left refracting surface, we can write it as mu, let us say this refractive index is mu2 and the refractive index outside is mu1, right? Here we have mu1. So mu2 by V1 minus mu1 by u is equals to mu2 minus mu1 by r1, right? Let us say r, so we have taken r1 as the radius of curvature of the left refracting surface. If you apply the same equation for the right refracting surface, in that case the u will become the v1, right? So this v1 basically, that is the object, and that is the distance of the object from the right reflecting surface. So we can say mu1 by v minus mu2 by v1 is equals to mu1 minus mu2 by r2. Got it? Now from these two equations, if we add these two equations, we'll get mu1 by v minus mu1 by u is equals to mu2 minus mu1 will be common. So 1 by r1 minus 1 by r2. Now let us rearrange. Let us take mu1 on the other side. So we have 1 by v minus 1 by u is equals to mu2 by mu1 minus 1 times 1 by r1 minus 1 by r2. And mu2 by mu1 is the refractive index of the lens material with respect to the, and mu2 by mu1 is refractive index of the lens material with respect to the surrounding. So we can write this as 1 by v minus 1 by u as mu 21 minus 1, 1 by r1 minus 1 by r2. So this, so what is left hand side? So if the object is at infinity, if u is minus infinity, then v will tends to focal length, right? So we can say 1 by f is equal, minus of minus infinity will be equals to mu2 1 minus 1 times 1 by r1 minus 1 by r2. So we can say 1 by f is equals to mu2 1 minus 1 times 1 by r1 minus 1 by r2. Now that is the lens maker's formula, and by using this formula, if we know the radius of curvatures of both the lenses, and if we know the medium refractive index of the lens material and the surrounding material, we can find the focal length of that lens, right? Because this right hand side is constant. It depends upon the geometry of the lens and the medium of the lens and the surrounding medium. So we can say 1 by v minus 1 by u is equals to 1 by f. So this is the lens equation, and this is the lens maker's formula, right? Now let us see some illustrations based on the concept that we have studied. Light from a point source in air falls on a convex spherical glass surface of refractive index 1.5 and radius of curvature 20 centimeter. The distance of the light source from the glass surface is 100 centimeter. At what position is the image formed? So we have given convex spherical glass surface. So this is a convex spherical glass surface, and we have given refractive index as 1.5. That is, this is mu2, and here we have air, right, which is mu1, which is equals to 1. And the object is placed at a distance, and the distance of the light source from the glass surface, this distance is given as 100 centimeter. So u is given as minus 100, and radius of curvature in this case will be positive because this will be the center of curvature. To measure the radius of curvature, we have to travel in the direction of the incident ray. So r will be plus 20 centimeter. So now we can apply the formula of reflection at a spherical interface. So mu2 by v minus mu1 by u is equals to mu2 minus mu1 by r. So let us substitute the value. So mu2 is 1.5 by v minus mu1 is 1, and u is minus 100. So 1.5 minus 1 divided by r will be positive, so plus 20. So this will become 0.5 by 20, so 1 by 40. So from a 1.5 by v is equals to 1 by 40 minus 1 by 100. So the LCM will be 200. So this will be 5 minus 2. So it will be 3 by 200. So we can say 1.5 by v is equals to 3 by 200, and this will give us 0.5 here. So v comes out to be 100 centimeter. So that is the position of the image formed by this spherical interface. Right, now let us see the different types of lenses. So we can categorize lenses in multiple ways. So the one way to categorize is as convex and the concave lens. Let us see the convex lens. So convex lens are of three types: biconvex, plano-convex, and we can say concavo-convex. So what are convex lenses? They are thick at the center and thin at the edges. So this is a typical convex lens, right? Biconvex lens. So both surfaces are convex, and this is the case of plano-convex, right? And for concavo-convex, we can say it will be something like this. Can you see all these lenses are thick at the center and thin at the edges? So this side is concave and this side is convex. And again, it is thick at the center and thin at the edges. Now let us see the example of concave lenses. Similarly, we can categorize concave lenses in three types: biconcave, plano-concave, and convexo-concave. So concave lenses are thin at the center and thick at the edges. So biconcave will look like this. Plano-concave will look like this. And convexo-concave, we can say it will be something like this, right? Which is thin at the center and thick at the edges. This side is convex, this side is concave. Right, so how we can check whether the lens is converging or diverging? So first let us write down the lens maker's formula. So 1 by f is equals to mu 21 minus 1 by r1 minus 1 by r2. Now in this formula we have two terms, two factors you can say, right? So we have mu 2 minus 1, mu 2 1 minus 1, and we have 1 by r1 minus 1 by r2. Let me call this as a and this as b. Now if a is greater than 0 and b is greater than 0, then focal length comes out to be positive. If focal length is positive, we can say it is a converging lens. If a is negative and b is negative, again we can say the focal length will be positive, so we'll get a converging lens. And if a is positive and b is negative, then focal length comes out to be negative. If a is negative and b is positive, again focal length comes out to be negative. So this is the case of diverging lens. Now let us see, when do we have a positive? So a will be positive if mu2 is greater than mu1, right? It means when the lens material is denser and the surrounding material is rarer, then we can say the factor a will be positive. And 1 by r1 minus 1 by r2. So 1 by r1 minus 1 by r2 will be positive in case of our convex lenses, and 1 by r1 minus 1 by r2 will be negative in case of concave lenses. So do remember this, and you can check this quite easily. So let me take a very simple case of, say, biconcave lens, right? So in case of biconcave lens, this is R1 and this is R2. So the center of curvature for R1 will be to the left and the rays are coming in the right direction. So R1 will be negative. And similarly, the radius of curvature for the right spherical interface will be in the right direction. So R2 will be positive. So can you see R1 is negative and R2 is positive. So 1 by R1 minus 1 by R2 comes out to be negative. So like this, similarly, we can check for the convex lens. This factor will come up to be positive for convex lens. So this way we can check whether the lens is converging or diverging. So lens formula we have already seen, and now let us see the magnification. So let us say there is a convex lens and this is the object. And this is the focus. So I'm considering a ray which is parallel to the principal axis and it is passing through the focus. I'm considering one ray which is passing through the optical center. This is the optical center and this is the image. So this is AB and this is, say, A prime, B prime is the image. This distance is U, this distance is V. Now, if this is height of the object, this is height of the image, then in order to find the magnification, we can use these two similar triangles. So we can say h naught by u will be equals to hi by v. So we have height of the image divided by height of the object as v by u. Now let us apply sign convention. Since image is to the right, so we have to travel in the right direction to measure the distance of position of the image. So v will be positive and u will be negative. So we can so by applying sign convention, and the image is also inverted, right? So hi is also negative. So minus hi by h naught is equals to v upon minus u. So hi by h naught comes out to be v by u, and hi by h naught is nothing but the lateral magnification. So this is the formula, and 1 by v minus 1 by u is equals to 1 by f. So this is the lens formula, and magnification is v by u. So do remember this, and do practice all ray diagrams which are applicable for convex lens and the concave lens, which we have already studied in class 10th. Right, now let us see the combination of lenses. So if we have say if we join two lenses together, let us say there is a concave lens, and we have placed it very close to say another lens which is convex, and let us say its focal length is f1, its focal length is f2. Then we can define the equivalent focal length, effective focal length, as 1 by f1 plus 1 by f2, because their powers are getting added up. So what is power? So power is defined as the reciprocal of the focal length. So p1 for the first lens it will be 1 upon f1, and for the second lens it will be 1 upon f2. And do remember, in case of a converging devices, power is positive. In case of diverging devices, power will be negative. So what are converging and diverging devices? So let us see. So converging devices, so we have concave spherical mirror, and or we can say converging lens. Similarly, diverging devices, we have convex spherical mirror or diverging lenses. Got it? So for diverging converging devices, power is positive. For diverging, it power will be negative. So for example, let me just take an example. So we have given a diverging lens of focal length, say 20 centimeter, and it is connected, it is joined with a converging lens of focal length, say 60 centimeter. So if I want to find the effective power, so we can say P effective will be P1 plus P2, and P1 will be, since we have a concave lens and the surrounding medium is rarer, it is a diverging lens. So we can say the power will be negative. So minus 1 by 20, and the second lens is converging, so the power will be 1 by 60, which is positive. So the LCM will be 60, so minus 3 plus 1, so that will be minus 1 by 30. Now the effective power comes out to be negative. It means the combination behaves like a diverging lens, right? So the focal length, effective focal length will be 1 by 30. Got it? So effective focal length will be 30 centimeter, and it is a diverging lens. So do remember this concept. A convex lens is placed in contact with a plane mirror. A, a point object is at a distance of 20 centimeter on the axis of this combination, has its image coinciding with itself. What is the focal length of the lens? Let us see. So there is a plane mirror, and over this plane mirror we have placed a convex lens. It's a thin convex lens, right? Now, in order to form the image on the object itself, the rays after reflection from the mirror should retrace their path. So it means the rays should hit the plane mirror normally. So if this is the object, and if I show the rays, we can say after refraction through the mirror, the rays will be parallel to the principal axis. So if this is the rays, if this is the principal axis, then the rays after reflection from the mirror should be parallel to the principal axis, and they will hit the plane mirror normally. Got it? So only in this case we'll be able to form the image at the object itself. So it means If the rays are getting parallel after refraction from the mirror or converging lens, then we can say the object must be placed at the focal length. So the object distance from the lens should be f, and f is given as 20. So point object is at a distance 20 centimeters. So focal length of the lens will be 20 centimeters. So that is the answer of this question. A convex lens has 20 centimeter focal length in air. What is the focal length in water? So we know the formula of lens maker's formula. So 1 by f is equals to mu 2 by mu 1 minus 1 times 1 by r1 minus 1 by r2. So convex lens has it has a focal length 20. So in air, mu1 will be 1 and mu2 is glass. Refractive index of air glass is 1.5. So that is 1.5. So 1 by 20 will be 1.5 by 1 minus 1 times 1 by r1 minus 1 by r2. Now from this equation we can find the value of 1 by r1 minus 1 by r2. So this comes out to be 1.5 minus 1.5. So this will be 1 by 2. And here we have 1 by 20. So 1 by r1 minus 1 by r2. So 1 by r1 minus 1 by r2 will be 1 by 10. So that is the first equation. Now, if we apply lens maker's formula, if the lens is surrounded by the water and water has a refractive index 1.33. So in water, mu1 will be 1.33 and mu2 is nothing but 1.5. So we have 1 by f is equals to 1.5 and we have 4 by 3, right? 1.33 can be written as 4 by 3 minus 1 and 1 by r1 minus 1 by r2 is nothing but 1 by 10. Now from this we have 4.5 by 4 minus 1 times 1 by 10. So this will be 0.5 by 4, 40, right? 0.5 by 40, which is 1 by 80. So the focal length of the lens in water will be 80 centimeter. So that is the answer. Now let us do the next question. A concave lens of refractive index 1.5 is immersed in a medium of refractive index 1.6. What is the nature of the lens? Okay, so 1 by f is equals to mu2 1 minus 1 by r1 minus 1 by r2. Now we have a convex lens. So in case of a convex lens, this second factor is negative. And since the lens is placed in a denser medium, then this factor is also negative. So if we have negative and negative, it becomes positive. So focal length will be positive. So it means it is behaving like a converging lens. Next question. A biconvex lens made of a transparent material of refractive index 1.25 is immersed in water of refractive index 1.33. Will the lens behave as a converging or a diverging lens? So I'm leaving this question as a homework because we have already covered the same concept. So try to do this right on your own. Right, so now let us see the next illustration. So when red light passes through a convex lens is replaced by light of blue color, how will the focal length of the lens changes? So when we had discussed a dispersion of light, then we have studied that the refractive index for a material for violet light is greater than the refractive index for the red light. So we can say refractive index for red will be less than refractive index for blue. So if that is the case, if I write lens maker's formula, so 1 by f is equals to mu2 by mu1 minus 1 times 1 by r1 minus 1 by r2. So when we change the color of the light, the second factor will not change, only the first factor will change, this mu2. So when we replace from red to blue, this mu2 will increase, right? So mu2 will increase. If mu2 is increased, so we can say this term, the first factor will increase. If first factor is increasing, then we can say focal length will decrease. Is it clear? Because focal length is, you can say it is inversely proportional to the first factor, and the first factor is increasing. If it is increasing, focal length should decrease. So under what condition does a biconvex lens of glass having a certain refractive index act as a plain glass sheet when immersed in a liquid? So a plain glass sheet has an infinite focal length because it does not bend the light. So we can say f should be infinity, right? To have f infinity, what we can say, 1 by f should tend to 0. To make it 0, mu to 1 minus 1 should be 0. So what does it mean? Mu 2 by mu 1 should be equals to 1 and mu 2 is should be equals to mu 1. So the refractive index of the material of the lens should be same as the surrounding material. Only in that case, it will be having focal length infinity. Got it? So the liquid should be having refractive index same as the refractive index of the material of the lens. Right, so now let us see the next question. So two thin lenses of power -4 diopter and 2 diopter are placed in contact coaxially. Find the focal length of the combination. So we have to use effective power formula, right? So it will be P1 plus P2, and power is measured in diopter, right? And one diopter is 1 meter inverse. So P1 is -4 diopter and P2 is 2 diopter, so it will be -2 diopter. Now P effective is, so basically the combination is behaving like a diverging lens. We have to find the focal length of the combination. So 1 by F equivalent will be -2 and F effective will be -1 by 2. So this is in meters, right? So to convert this into centimeters, we have to multiply with 100. So focal length will be 50 centimeter. Right. So a glass lens of refractive index 1.5 is placed in a trough of liquid. What must be the refractive index of the liquid in order to make the lens disappear? Again, it is the same question as this one. The refractive index of the material of the lens should be same as the surrounding material to make the lens invisible in that liquid. An equiconvex lens of focal length f is cut into two identical plano-convex lenses. How will the power of each part be related to the focal length of the original lens? Now let us see. So we have equiconvex lens. It means both the surfaces will be having same radius of curvature. Now we have split this lens into two parts, right? So this is one of the part. Now let us find the focal length of both these, right? So let us say it has a focal length f. So 1 by f will be equals to, let us say refractive index is mu and surrounding is air. So mu -1 times, and this comes out to be 2 by r. Let us say r is the radius of curvature of both the surfaces. And so from here, f comes out to be r upon 2 mu -1. Now let us say it has a focal length small f. So 1 by f is equals to mu -1 times 1 by r. So focal length will be r upon mu -1. So we have to, how will the power of each part be related to the focal length of the original lens? So focal length of the original lens, so r upon mu -1 is 2 times f. So small f will be 2 times f. So it will be double, right? So focal length becomes double. A double convex lens of +5 diopter power is made of a glass of refractive index 1.55 with both faces of equal radii of curvature. Find the value of its radius of curvature. So we can apply lens maker's formula. So 1 by f. So here so power, this is given as 5, right? So 5 and this power is in meter inverse. So this is 5 equals to mu 1.55 minus 1 times 2 by r. Now from this we can say r will be 2 times 0.55 by 5. So this will be 0.11 meters. So this answer will be in meters. So it will be 0.22 meters, or we can say 22 centimeters. So that is the answer of the second part. Now let us see another question. A beam of light converges at a point P. A concave lens of focal length 16 centimeter is placed in the path of this beam 12 centimeter from P. So there is a point P and there is a converging beam, and they converge at point P. Now what we have done, we have placed a concave lens in the path of the beam at a distance 12 centimeter from the lens or from the point P. So this is 12 centimeter and the focal length of the lens is 16 centimeter. Now draw the ray diagram and find the location of the point at which the beam would now converge. Right, so since it's a diverging lens, so it will diverge these rays. So it means the rays will get diverged and they will again coincide at a distance which is greater than 12 centimeter. Let us say this distance is V and this is U and this is the direction of incident ray. So U will be positive, so it will be plus 12 centimeter. V, we have to calculate. Focal length, since it's a diverging lens, its focal length will be minus 16 centimeter. So we can apply lens formula. So 1 by F is equals to 1 by V minus 1 by U. So 1 upon minus 16 is equals to 1 by V minus of plus 12. So 1 by V is equals to 1 by 12 minus 1 by 16. So the LCM will be 48. So this will be 4 minus 3. So 1 by 48. So V comes out to be 48 centimeter. So now the rays will converge at a distance 48 centimeter from the lens. Okay, right. Now let us see this question. A radial curvature of faces of double convex lens are 10 and 15. If the focal length of the lens is 12 centimeter, find the refractive index of the material of the lens. We have done similar questions, so do this question as a homework. Right. Let us see this question. In the following diagram, an object O is placed 15 centimeter in front of the lens 1. So this is the object O, which is placed at a distance 15 centimeter from the lens 1 of focal length 20 centimeter. And the final image is being formed at I at a distance 80 centimeter from the second lens. Find the focal length of lens 2. Right. So if you look at the image formed by the first lens, so let us find that image, right? So we can apply, so first lens, if you apply lens formula, so we can say 1 by V. So U is minus 15 centimeter. Focal length is 20 centimeter. So 1 by V is equals to 1 by U plus 1 by F. So 1 upon minus 15 plus 1 by 20. So LCM will be 60. So minus 4 plus 3. So this will be 1 by 60. So V comes out to be minus 60 centimeter. So it means this distance is 60 centimeter. Now this image formed by the first lens will act as the object for the second lens. So for second lens, we can say U will be minus 60 plus 20, right? That is the distance of the image formed by the first lens from the second lens. So it will be minus 80 centimeter. Focal length of the second lens we have to calculate. And image distance is given to us, that is plus 80 centimeter, because it is in this direction, right? In the direction of the incident ray, we have to measure the distance, which is positive. So we can say 1 by V minus 1 by U is equals to 1 by F. So 1 by V is given, V is 80 minus of minus 80 is equals to 1 by F. So which comes out to be 1 by 40. So focal length will be 40 centimeters. So that is the answer of this question. A convex lens of focal length 20 centimeter is placed coaxially with a convex mirror of radius of curvature 20 centimeter. The two are kept at 15 centimeter from each other. So we have a convex lens and there is a convex mirror, and they are kept at a distance of 15 centimeter. And the radius of curvature of convex mirror is 20 centimeter and focal length of the lens is 20 centimeter. A point object lies 60 centimeter in front of the convex lens. So there is an object which is placed at a distance of 60 centimeter in front of the convex lens. Draw the ray diagram to show the formation of the image by the combination. Determine the nature and the position of the image. Okay, right. So let us draw the ray diagram. Before that, let us find what is the position of the image formed by the lens. So if I draw lens formula, so 1 by V minus 1 by U will be minus 60 and focal length is 20. So 1 by V is equals to 1 by 20 minus 1 by 60. LCM is 60, so this will be 3 minus 1, so it comes out to be 1 by 30. So V comes out to be 30 centimeter. So if I draw ray diagram, the image will be formed at a distance 30 centimeter in front of the lens. Now this image 1 act as the object for the spherical mirror. Right, so now let us apply mirror formula, and this distance is 15 centimeters. So we can say U will be plus 15 and focal length will be plus 10 because radius of curvature is given as 20. So 1 by V plus 1 by U, that is 15, is equals to 1 by F, which is 10. So 1 by V is equals to 1 by 10 minus 1 by 15. So LCM is 30. So 3 minus 2. So V comes out to be 30 centimeter. So it means, and it comes out to be positive. So what does it mean? So it means the rays are reflecting like this, and the image is being formed somewhere here, and this distance comes out to be 30 centimeter. Now this is I2, and this I2 will act as the object for the lens again, and this is the direction of incident ray now. Now again let us consider lens. So U will be 30 plus 15 is 45, so we can say it will be minus 45 centimeter. Focal length is 20, so 1 by V minus 1 by U, that is minus 45, and 1 by F, that is 1 by 20. So 1 by V is equals to 1 by 20 minus 1 by 45. So LCM will be 180. So that will be 9 minus 4. So this will be 5 by 180. So it comes out to be 1 by 36. So V is 36 centimeters. So it means after that this ray will converge at a point which is 36 centimeter. So that is the ray diagram. So I hope this concept is clear. Right. So now let's see one more question. You are given three lenses L1, L2, and L3, each of focal length 20 centimeter. An object is kept at 40 centimeter in front of lens L1 as shown. So focal lengths are given, each is having focal length 20 centimeter. The final image is formed at the focus I. So this is 20. So it means the rays between L2 and L3 should be parallel, right? Parallel to the principal axis. Only in that case they will converge at focus. Got it? So let us first find the image position by the lens 1. So we can, so 1 by V minus of minus 40 is equals to 1 by 20. So 1 by V is equals to 1 by 20 minus of 40. So this will be 1 by 40. So V comes out to be 40 centimeter. So what we can do, if this is lens 1 and this is the object and the image is being formed at a distance which is 40 centimeter, and there is a convex lens, and after that the rays becomes parallel to the principal axis. So it means the image should be at the focus, right? So this has to be equals to the focal length. So this distance has to be 20 centimeter. So it means the distance between L1 and L2 should be 60 centimeter. Find the separations between L1, L2 and L3. So in case of L2 and L3, we can have any distance because the rays are parallel to the principal axis. So it can be any distance between L2 and L3, but in L1 and L2, it has to be, we can say 60 centimeter. So that we should remember. So L1, L2 should be 60 centimeter, and L2, L3 can be any distance. Right. So here I conclude ray optics, but I will cover optical instrument in a separate video. So see you in that video. Thank you.